everyone. Myself, Dr. Vishnu Sharan Das, welcome you to Chemistry Works and my video series on phase rule. Today I have to discuss one component sulphur system. So first of all, let us know the physical forms of sulphur. You know, when one substance, existence of a given substance in a more than one crystalline form possessing different physical properties is known as polymorphism. Okay. So this polymorphism is exhibited by the elements and the compounds. When the compound exhibits the polymorphism, it is okay. But for element, the polymorphism is known as allotropy. Okay. So your sulphur exists in 6 allotropic forms, that is 6, 2 in crystalline form and 4 in amorphous form. So these 2 crystalline forms are rhombic sulphur and the monoclinic sulphur, and 4 amorphous sulphurs are there. When 2 allotropes can change reversibly. Here, rhombic sulphur and monoclinic sulphur, this is the transition temperature. So at transition temperature, rhombic sulphur changes to monoclinic sulphur and the monoclinic sulphur changes to rhombic sulphur. So this is called enantiotropy. But your white phosphorus and red phosphorus are 2 allotropes. The white phosphorus changes to red phosphorus, but the reverse change cannot be possible. And the diamond graphite are also allotropes, and the diamond changes to graphite, but graphite cannot change to the diamond. So this type of change is called monotropy. Okay. So your sulphur exists in the 2 crystalline forms. We are for the phase diagram, we are considering this crystalline forms. Okay. So we have 4 phases of the sulphur, that is rhombic sulphur, monoclinic sulphur, Al liquid sulphur, and Sb sulphur vapor. So we are considering the 4 phases of the sulphur. So we will consider the mathematics of the phase rule. That is, the 4 phases are there. The 2 phases equilibrium. How many number of 2 phases equilibriums are there? So we calculate the 4C2. Out of 4 phases, 2 phases taken at a time. That is 4 factorial by 4 minus 2 factorial into 2 factorial is equal to 6. So again, how many number of 3-phase equilibriums are there? So this will be the 4C3 is equal to 4 factorial by 4 minus 3 factorial into 3 factorial, this is equal to 4. So maximum 3 phases can coexist at 4 different points, and 2 phase equilibrium at 6 different curves or lines. So let us take a 4 phases coexist how many times? So 4C4 this is equal to 4 factorial by 4 factorial into 4 minus 4 factorial, this is equal to 1. So theoretically we can say the 4 phase coexistence, that will be 1 point, but as far as this phase rule is known, F is equal to 2 plus C minus P is equal to 2, and it is 1 component, 4 phases, so this is equal to minus 1. So degree of freedom is minus 1, which is impossible. So this phase rule excludes for 1 component system, the 4 phases cannot coexist. The 4 phases cannot coexist at any point. Okay. So this is the mathematics. From mathematics we have 6 binary equilibriums and 4 ternary equilibriums, that is the triple points in the phase diagram. Now let us proceed to the phase diagram and identify the different binary equilibriums. So SR, SN, SL, SV, and let us write 6 binary equilibriums as SR equilibrium with the SM, SR equilibrium with the SL, SR equilibrium with the SP, again SL equilibrium with the SP, SL equilibrium with the SL, SL equilibrium with the SP. Okay, so theoretically we have written all the six taking these 4 phases, and now we identify which one is what chord. So this portion is your solid rhombic, and this is monoclinic sulfur, and this is liquid sulfur, and this region is your sulfur vapor. So say A to B, this is the sublimation chord, the rhombic sulfur chain, and your sulfur vapor equilibrium. Okay, so SR, SV equilibrium. So you see SR, SV. So this line is AB. Your AB is the sublimation chord of rhombic sulfur vapor. Then BC. So BC, this is the equilibrium of SM, SV. So SM, SV, this is your BC chord, and CD chord, this is the vapor pressure chord. So SL, SV. So SL, SV, this is your CD chord. This is the vapor pressure chord of the sulfur. And let us consider the CE. So monoclinic sulfur changes into the liquid sulfur SMSL. So SMSL, this is your CE chord, and the BE chord, which is the transition of SR to SL, that is say BE chord. Okay, so this is the equilibrium of SR-SL, and one more, it is left SR-SL. So EF, that is your EF is the SR-SL. Okay, so this is the EF. So we have mapped these binary equilibriums in the phase diagram. Okay, so now let us consider the 3 phase equilibriums in this phase diagram. See, so the 3 phase diagram, 3 phase equilibrium, that will be the, how can we find mathematically, and that we will plot in the graph. So SR, SL, SL, 1, SR, SL, SV, SL, SL, SV, equilibrium. So one more is there. So let us find SR, SL, SL, SR, SL, SL. Okay. So SR, SL, SL, this one. This is the SR, SM, SL. So this is the triple point E. So this point is your E. Okay. Then the point B, that is SR, SM, SB, SR, SM, SB. So SR, SM, SB, that is point B. Again, point C, it is the SL, SL and SB, SL, SL, SB. So this is point C. So with the 3 triple points we have mapped successfully, and SR, SL, SB, it is not found in this curve. And this is the metastable equilibrium. We will find it later. Okay. So now let us study the effect of pressure, temperature, and separately and combined. So let us study the graph again. So this is a two-dimensional plot, pressure versus temperature, and here is your sublimation curve, that is the SR to SR equilibrium only, SB, and this is the transition equilibrium, SR, SM, okay. And this is your second sublimation, that is SL, SB. Okay, this is vapor pressure curve, CD, and this is fusion curve, CE is your fusion curve, and EA is also the fusion curve. So this is fusion curve of monoclinic sulfur, and this is fusion curve of rhombic sulfur. Okay. So these are the physical phenomena. So if you find the region, that is the E, B, A, or A, B, E, this is the region of SR solid. Okay. And B, E, C, this is the region of SL solid. And A, B, C, D below A, B, C, D, A, B, C, D, that is SB, sulfur vapor, and A, B, C, D, A, B, C, D, this is SL, liquid sulfur. Okay. So now we will see the effect of the pressure and temperature on the phase diagram. So as we have learned, the rhombic sulfur changes to monoclinic sulfur at this 95.6 degrees centigrade. Okay. Suppose we have taken the rhombic sulfur at 1 atmosphere and supplied heat, keeping the pressure constant. So this is the enclosed in a piston. So role of piston is to maintain the pressure constant. So keeping the pressure constant, we have supplied heat, and the temperature is rise, and at this temperature, this rhombic sulfur changes to monoclinic sulfur. And if you continue supply heating, then at this point, the total rhombic sulfur will transfer to the monoclinic sulfur. Then, if heating is continued, then the temperature will rise up to this, and here it will stagnate to the liquid sulfur. Okay. So, as it is seen from the graph, that at constant temperature, at constant pressure, if we heat, then the rhombic sulfur changes to monoclinic sulfur, and the monoclinic sulfur changes to the liquid sulfur at the melting point, and at 434, the liquid sulfur changes to the sulfur vapor, SB. Okay. So this is the effect of temperature at constant pressure. So if we analyze this graph, you see A, B, B, C, C, D, C, E, and BEF. All the curves have positive slope. Okay, they have positive slope. So from the Clapeyron equation, dP by dt is a positive. So this indicates if we increase the pressure, then temperature will increase. If we increase the pressure, the temperature will increase. If you decrease the temperature, the pressure will increase. Okay? So, because this is explained by the Clapeyron equation. Also, we have the density of rhombic sulfur, SR, is greater than the density of monoclinic sulfur. And also, we can say the volume of SR is less than the volume of SL. Okay? So, this all these explains, supports this Clapeyron equation. If we increase the pressure, then the temperature will increase. Say, we have taken rhombic sulfur and we are increasing the pressure and the temperature will automatically increase. So, when 95.6 degree centigrade will be reached and at a pressure of 0.01 mm mercury, then here in addition to the rhombic sulfur and sulfur vapor, the another substance starts burning, that is a monoclinic sulfur. Okay. Again, from this point, if we increase the pressure and increase the temperature will increase, okay, and we proceed in this line. So the conversion of rhombic sulfur to monoclinic sulfur will be faster, and the formation of sulfur vapor is stopped in this line. So this is called the transition curve, rhombic sulfur to monoclinic sulfur. And you see, the transition temperature TE is proportional to the pressure. If the pressure increases, the transition temperature increases. Okay? So also this pressure increases, the sublimation temperature increases. So this is sublimation curve of rhombic sulfur, this is sublimation curve of monoclinic sulfur. And when the pressure increases, the sublimation temperature increases. Also, in this curve you see, when pressure increases, the boiling point of this liquid sulfur also increases. And also you consider this curve, the fusion curve of the fusion curve of monoclinic to liquid sulfur. And if we increase pressure, then the fusion temperature also increases. Okay, so this is the effect of temperature and pressure on the phases of different type. So if we consider a point here, and at this point, if we increase the pressure, keeping temperature constant. Suppose we have increased in this line, the pressure is increased, keeping the temperature constant. So what will happen? The monoclinic sulfur will get the point here, so the point will shifted to here at higher pressure. So the monoclinic sulfur will convert to the rhombic sulfur. Okay? And again, if you want to transform the attain the equilibrium again, then we have to supply heat to reach at this point. Okay? So this is supported by the Lee-Chatterjee principle to explain any sort of equilibrium. When stress is applied, pressure is increased, so we have to adjust the temperature. The temperature should be adjusted in order to attain the equilibrium. Okay, so this is the effect of temperature and pressure on the different curves and lines. So now let us calculate the degree of freedom for this line, and before calculating the degree of freedom, let us find the metastable equilibrium. We have already left one equilibrium SR, SL, SV. SR, SL, SV is left unmapped. So this is the EF is the fusion curve of SR, that is rhombic sulfur changes to the liquid sulfur. So if you do the reverse process, that is if you cool it, and the cooling is faster. So instead of getting this triple point, where the monoclinic sulfur is to be formed, we will associate in this line to here. Okay, up to this point, without forming the solid monoclinic sulfur. Okay, the solids rhombic sulfur and the liquid sulfur equilibrium will continue up to this. Again, this is the vapor pressure curve or the melting point curve, melting curve of the liquid to vapor, and if we cool it, and the cooling is faster, then instead of getting point C, at point C we have to get the liquid sulfur, sulfur vapor and the monoclinic sulfur. This point will be extended to this point, okay, and without burning the monoclinic sulfur at here. So we are proceeding because of the rapid cooling process. The rapid cooling process, we are entering the territory of monoclinic sulfur without getting monoclinic sulfur. Again, this sublimation curve, we are supplying heat and increasing pressure. So at point B, the triple point, that is SR, SL, is reached, but the heating is so fast that if we heat it so fast, then instead of getting this point, we will continue the equilibrium SR and SB up to this. Say this point is called O. Okay, so this is called the metastable equilibrium, and at this point, if you make any change or give a slight jump to this point, then the total substance, solid, liquid, vapor, all types of sulfur, the three types of sulfur will be converted to the solid monoclinic sulfur. So this is the metastable equilibrium, that is this point is O, we have that, and here we have the OE, your OE, it is the equilibrium of the SR and SL equilibrium, the metastable equilibrium. Again, the BO line, BO curve is the metastable equilibrium of the SR, SR, SB, and the OC, it is the equilibrium of the SL, SB equilibrium. Okay, so these are all metastable curves, and the region EOB, this is EOB, is the metastable SR metastable. This is solid metastable. Okay, SR solid rhombic metastable portion. So EOC, this is the EOC, this is the metastable SL, and BOC, this is the metastable SB. Okay, so this explains the metastable. So metastable is achieved by cooling. Okay, in this case it is cooling, and in this case it is cooling, but in sublimation curve it is heating. Okay, and the metastable equilibrium is one directional equilibrium. It is achieved in one direction. From the reverse direction it cannot be achieved. It cannot be achieved from both the sides equilibrium. So it is called the metastable equilibrium. Now we will calculate degree of freedom for different curves, points, and the region. So from the basics of the phase rule, we have F max is equal to 1 plus C, and the F minimum is equal to 0. So F max is equal to 2. So maximum degree of freedom is 2, and F minimum is equal to 3. And from this phase rule, that is F is equal to 2 plus C minus P. We can write this F plus P is equal to 2 plus C. So always for all points, degree of freedom plus number of phases is equal to 2 plus C, that is 3. So when F is equal to 2, that is a degree of freedom maximum is equal to 2, the phase is equal to 1, and if minimum F is equal to 0, then P is equal to 3. Okay. So maximum number of phases, that is 3, that can coexist. So we have these points, that is B, C, O and E. These are the triple points. So the point B, O, C and E, these are called triple points. So 3 phases coexist. So these points are called invariant, as the degree of freedom is 0 at these points. Now let us take a point on the chord. Okay, there are so many chords: A, B, B, C, C, D, C, F, B, E. So many chords are there, and each chord has its own identity: sublimation chord, transition chord, fusion chord, vapor pressure chord, etc. So if we take a point on the chord, that is the equilibrium, 2 phase equilibrium. So when P is equal to 2, C equal to 1, the F is equal to 2 plus 1 minus 1, that is the 1. So the degree of freedom is 1. When F is equal to 1, it is called monovariant. Monovariant. Okay. So invariant and monovariant. If you take a point in the region other than these chords and points, say here or here or here, okay, then this is a single phase. So for isolated single phase, the degree of freedom we calculate as F is equal to 2 plus C minus 3, that is 2 plus 1 minus 1 is equal to 2. So we take any point in this region or in this region or in this region or in this region. So it is pure vapor phase, this is pure liquid phase, and this is pure monoclinic sulfur solid, and this is a pure solid rhombic sulfur. So for this, the degree of freedom is equal to 2. So when degree of freedom is 2, it is called bivariant. Okay. So in this way, we have calculated the degree of freedom for the different parts of the chord. Okay. So now let us summarize the whole topic. Say at extremely low temperature and high pressure. Extreme low temperature means somewhat here, okay, in this region. So extreme low temperature and high pressure, we will get the solid rhombic sulfur. Okay, and reverse, extreme low temperature and low pressure, low temperature and low pressure. So we will get the vapor, sulfur vapor will be obtained, and low pressure, high temperature, we will get the sulfur vapor. Okay, so at high temperature and high pressure, you will get this liquid sulfur, and in the medium range you will get the monoclinic sulfur. Okay, so at low temperature and low pressure there will be the equilibrium between the rhombic sulfur and monoclinic sulfur. So in this way, and if you consider, so this is the your transition point, transition chord. So this is the transition temperature, and if you see the chords, all the chords or lines have positive slope. So your dP by dt is positive. So this shows that the transition temperature T transition is proportional to pressure. So if we increase the pressure, the transition temperature will increase. So if we increase the pressure, the transition temperature will. If we increase the pressure, the sublimation temperature will increase. T sublimation is proportional to pressure. Then fusion. This also shows the T fusion. Temperature of fusion is also proportional to the pressure. If fusion temperature will increase, then pressure will increase. And vapor pressure. So this is the vapor pressure curve. Also, T boiling point is proportional to vapor pressure or pressure. Okay. If the boiling point will increase, vapor pressure will increase. If vapor pressure will increase, then boiling point will increase. So this is the summary we have reached from study of the phase diagrams of sulfur. Thank you for your patient watching, and I hope you will subscribe and share to my channel. Thank you again.